Hi, so today we will be discussing the Euclidean algorithm as well as Bezos' identity. So let's get started. Okay, so the Euclidean algorithm. Okay, what's the Euclidean algorithm? The Euclidean algorithm is a method for computing the GCD of two integers. Okay, then what is the GCD? If we say GCD, this refers to the greatest common divisor of two integers. Okay, quickly an example. So GCD of 27 and 51. By the way, you'll indicate 51. Well, you'll indicate the GCD with these rounded brackets. You could also just use the rounded brackets instead of indicating the GCD at the front. So 27 is equal to 3 to the power of 3. 51 is 3 times 17. So this answer is going to be 3. 3 divides both of them. There's no other bigger common divisor, bigger divisor that will divide both of them. Okay. Next, let's look at the LCM. It is the least common multiple. Okay, so if we say, so whereas with GCD we indicated it with rounded brackets, with LCM we will use square brackets. So the LCM of 12 and 16 will be equal to 48. You can also just indicate it as such. We know this since 12 is equal to 2 to the power of 2 times 3, and 16 is 2 to the power of 4. Okay. Now a quick formula to use for the LCM. So we said that we're going to use the Euclidean algorithm to calculate what the GCD is. Once we have the GCD, we can use a formula to see what the LCM will be. So this formula states that the LCM of A and B is going to be AB over GCD AB. Okay, quickly another definition. If we say two numbers are coprime or relatively prime, relatively prime, so if integers A and B are coprime, this means GCD of A and B will be equal to 1. So they share no common factors except for 1. So an example would be 27. Example would be 27 and 26. Since 27 is 3 to the power of 3, 26 is 2 times 3. They share no common factors or non-common prime divisors. So GCD of 27 and 26 is going to be equal to 1. Okay, so now for the Euclidean algorithm, or the method there for it. Okay. Method. Okay, so firstly we're going to note that if we have some integer a and some natural number b, then we can write a as being equal to b times q plus r for some unique q and r integers, so integers q and r. Another thing to note, where r is going to be smaller than b. Okay, so what we would call each of these, b would be known as the divisor. So b is dividing a so that we arrive at a remainder. And then we also have the quotient. So quickly look at an example. So if a were to be 35, we would say, and we would divide, not 35, 37. If we were to divide 37 by 5, we would have 5 times 7 plus 2. So this is a, this is b, this is q, and r is 2. R is 2, yeah. Okay, so we're going to remember this, and what we want to do now for the Euclidean algorithm. So we want to know the GCD of a and b, where a is bigger than b. So what we're going to do is we're going to say, okay, let's write a as being, let's write a is equal to b q1 plus r1. So it's, we divide a by b, it's going to leave some remainder r1. Then what we do is we do this again, but now we're going to move these numbers over. So we're going to do this with new numbers. So now we say b is equal to r1 q2 plus r2. We do this again, and we say r1 is equal to r2 q3 plus r3. So what we're going to do is we do this over and over again until we reach some rk. So we would do this, we would repeat this, where rk plus 1, qk plus 2, plus rk plus 2, and then next one would be moving these values over. Is equal to rk plus 2 times qk plus 3 plus 0. So we repeat this until we reach 0. Repeat until remainder equals 0. Then the GCD of a and b will be equal to the last non-zero remainder. So it's going to be this rk plus 2. So let's quickly look at an example using these steps. So say we wanted to know the GCD of 51 and 297, GCD 297, 51. So 297 is bigger than 51, so we're going to say 297 is equal to 51 times 5, which is 255, so it's going to be plus 42. Then 51 is equal to 42 times 1 plus 9. Then again 42 is equal to 9 times 4 plus 6. Then again 9 is equal to 6 times 1 plus 3. 6 is equal to 3 times 2 plus 0. So we have reached 0, and what we did in every step is we took this value over and we repeated this step until we reach 0. So now that we've reached 0, this means that the GCD of 297, 151 will be equal to 3. Okay, let's do another example quickly. What would the GCD of 36 and 152? So 152 is bigger, so we're going to say, we're going to write 36 in terms of, or for 152, we're going to write 152 in terms of 36. So 152 is equal to 36 times 4, that's 144, plus 8. Then again, 36 is 8 times 4 plus 4. Then everything's over again. 8 is equal to 4 times 2 plus 0, and we've reached 0. So once again, we move these values over each time until we reach 0, which means that the GCD of 36 and 152 is going to equal 4. Okay. So let's quickly do a problem involving the Euclidean algorithm. Okay, so this problem states, so this is from 1959's IMO. You won't expect any IMO questions this easy anymore. So they tell us to prove that the fraction 221n plus 4 over 14n plus 3 is irreducible for every natural number n. So what does irreducible mean? Irreducible means simply that the top part and the bottom part is going to have a GCD of 1. So GCD 21n plus 4 and 14n plus 3 is going to equal 1. This is what we want to prove. In other words, they are going to have no other common factors except for 1. Okay, so let's try to calculate the GCD of these two terms according to the Euclidean algorithm. So since 21n plus 4 is bigger than 14n plus 3, we say 21n plus 4 is equal to 14n plus 3 times 1 plus 7n plus 1. So this is the remainder, or R1. Q1 is equal to 1. This is B, and this is A. You can, 14n plus 7 is going to be 21n, and 3 plus 1 is going to be 4, and that's how we reach the remainder of 7n plus 1. Let me do this once again. We say 14n plus 3 is equal to 7n plus 1 times 2 plus 1. So we move these over. Now what we have is 7n plus 1 is going to equal 1 times 7n plus 1 plus 0, and we have reached 0. Since we have reached 0, so once again, we did this over and over again. Since we have reached 0, this means that the GCD of 21n plus 4 and 14n plus 3 is going to equal 1. Okay. So yes, it's quite a nice and short question. And since we've now proven that the GCD of these two terms are going to equal 1, this means this whole expression, this whole fraction is going to be irreducible. And yes, so we are done with the question. Okay, now we're going to quickly look, at Bayes' identity. Okay. Bayes' identity says that let a and b be integers and let the GCD of AB equal D. Then there exists x and y integers xy such that ax plus by is going to equal d. Okay, so in other words, if we have a and b and we know that their GCD is d, so d can even be 1, it can be, can be d. It can be 1 or any other natural number, then it means that you can find some x and y, so you can find two integers that if you multiply one by a and the other by b, you will arrive at d, their GCD. Okay, so let's do another problem involving Bayes' identity. Okay, so this problem says let a and n be positive integers and a is not equal to 0. Prove that this is true. So as I said, so these rounded brackets, they just mean the GCD. So prove that the GCD of this expression and this expression is going to equal a to the power of the GCD of m and n minus 1. Okay. So how we're going to approach this, we're going to say let D equal the GCD of m and n. So this means m is going to equal some x1d and n is going to equal some x2d. You don't have to write this down, it's just to think about it. Okay. Then we're going to note that, so we're going to use the rule that if you take, if you have a number, if you have something like a to the power of b minus 1, you can rewrite this as being a minus 1 times a to the power of b minus 1 plus a to the power of b minus 2, and we can go on and on, plus 1. Let's write that out more fully. So a to the power of 2 is a to the power of 1. So just a plus 1. So we're going to apply this, but we're going to apply it to a to the power of m minus 1. So a to the power of m minus 1 is equal to a to the power of x1 d minus 1, which we can once again rewrite as being a to the power of b to the power of x1 minus 1, which when we apply to this formula, instead of taking, we now take a as being a to the power of d. So now this is going to be a to the power of d minus 1 and a to the power of d x1 minus 1 plus a to the power of d x1 minus 2, and on until we have a to the power of d to the power of 2 plus a to the power of d 1 and plus 1. So what we see here is, let's take this back, thus a to the power of d minus 1 will divide a to the power of m minus 1, since it is a factor of a to the power of m minus 1 if you factorize it as such. So similarly we show a to the power of d minus 1 is going to divide a to the power of n minus 1. So in the same way we would say n is going to equal a to the power of n minus 1 is going to equal a to the power of x2d minus 1, and we would follow all of these same steps. Okay. So what these two expressions mean, in other words, is that a to the power of m minus 1 is going to equal a to the power of d minus 1 times some y1, and a to the power of n minus 1 is going to equal a to the power of d minus 1 times some y2. So these two are some integers. Okay. Now, since we have this is true, and we have that this is true, we also know now that, so thus, a to the power of d minus 1 is also going to divide the GCD of a to the power of m minus 1 and a to the power of n minus 1. Okay, so you can think of it as, so the GCD of a to the power of n minus 1 and the GCD of a to the power of n minus 1 is going to be a to the power of d minus 1 times some other integer, which you can take out of y1. So, how do I explain this? So the GCD of two numbers is the biggest number that both can be divided by. And since we know a to the power of d minus 1 divides both of these, we know that the GCD is going to be a to the power of d minus 1 times some other integer. That's why we know a to the power of d minus 1 is going to divide their GCD. Now we take Bezos' identity. So by Bezos' identity, there is going to exist some x and y, part of the integers, such that nx plus ny is going to equal d. Also note that if x and y are both smaller or equal to 0, then d would also be smaller than 0, smaller or equal to 0, which would be a contradiction. So this would be a contradiction. You indicate a contradiction as such. Contradiction. Okay. Also, if x and y were to be both positive, then mx plus ny would be bigger than d. But this would not make sense. Oh, so they would be bigger than d since we know that the GCD of a number, since GCD of m and n equal to d is going to be smaller or equal to m and n. So if all of these ones if all of the numbers on this side is going to be bigger than d, or all of them are going to be positive, and we know m and m is also bigger than or equal to v, this would be a contradiction. So once again, we have a contradiction, which means since x and y, this is a contradiction, so both can't be positive and both can't be negative or non-zero. This means that, this implies that x and y have opposite signs. So let's assume that so when we say opposite signs, so one is going to be positive, the other one is going to be negative. So assume that x is bigger than 0 and y is smaller or equal to 0. So we're going to assume the one is negative or non-positive one, and we're going to assume the other one is the positive one. Then we have that, now we're going to say, let T be the GCD of a to the power of m minus 1 and a to the power of n minus 1. If you recall, we had that a to the power of d minus 1 divides GCD of a to the power of n minus 1 and a to the power of n minus 1. So now we have that this expression on the right hand side is equal to t. From this we say that, so using the same idea as before, we had that a to the power of b minus 1 is going to be a minus 1, a to the power of b minus 1 plus a to the power of b minus 2, on and on, plus 2, plus 1, 2, plus a plus 1. So we apply this again and we say a to the power of mx minus 1 will be equal to a to the power of m to the power of x minus 1. So this is going to be a to the power of n am times a to the power of m x minus 1, a to the power of m x minus 2, a to the power of m plus 1 and another bracket. So we do this again, but now we do it for a to the power of mx minus 1. So from this we see that, okay, so since we know the GCD, let's see from this expression first. So this means that a to the power of m minus 1 divides a to the power of mx minus 1. Since the GCD of a number divides the number itself, this means the GCD of of am and a to the power of n minus 1 is going to divide a to the power of m minus 1. So t, we've established that t is this GCD. So t divides am to the a to the power of m minus 1. Which means that t divides this whole expression. So now we have that since a to the power of m minus 1 divides this, we also have that t is going to divide a to the power of mx minus 1. Similarly, we can show that t is going to divide a to the power of nx or ny, well, a to the power of minus ny minus 1. So the reason we say minus ny is because we know y is not going to be positive. So since y is not going to be positive, instead of using doing this with x, we're going to use it with minus y, which can hold since y will then be a positive number. Okay. Since we know these two things, we also know that hence t is going to divide a to the power of mx minus 1 minus a to the power of d times a to the power of ny minus 1. So we've already established t divides this expression and t divides this expression. So t is going to divide this expression, and anything multiplied with that, it's not going to change the fact that it will divide this whole expression. So let's simplify this expression. So this is going to be a to the x minus 1 minus a to the power of d minus ny. So adding these exponents plus a to the power of d. Okay. Now we're supposed to remember that we had this mx plus ny is equal to d. So remembering that, let's put d in. So a to the power of mx minus 1 is equal to a to the power of mx plus ny minus ny plus a to the power of mx plus ny, which means that this will be a to the power of mx minus 1 minus a to the power of mx plus a to the power of, let's just write it as d again. So now you see this expression and this expression will cancel out. So those two terms will cancel out. And we are left with a to the power of d minus 1. So let's look at what the original question asked for. We wanted to prove, let m and n be positive integers, prove that the GCD of this and this is going to equal this. So what we now have is since t divides this, so let's rewrite this. So t divides a to the power of d minus 1. That is what we got from this. Which means if we want to rewrite t, t is equal to the GCD of a to the power of n minus 1. And a to the power of n minus 1, and this divides a to the power of the GCD of mn, since that is how we defined d. And we also had that we also had this. So along with this statement, we also had that a to the power of GCD mn minus 1 also divides GCD a to the power of m minus 1. So since these two divide, so the one divides the other and the other one divides the other, this means that the GCD of a to the power of m, so, right, since, and this GCD of a to the power of m minus 1 and a to the power of n minus 1 is going to equal GCD, a to the power of GCD m and n minus 1. So we know this since if you look at the properties for divisibility, we saw that if two numbers divide each other, it means that the absolute value of the other one will be plus minus the other one, but since we know both of these sides need to be positive, it just means that they will be equal to each other. And we have proven this statement. So that is all for today. If this may seem a bit confusing, feel free to ask more questions later this afternoon. Yes, thank you, and see you tomorrow.